In the last video, we discussed some of the equations for sums of series and sequence, and we also looked at equations that represent any given term in a series or sequence. And I promised that we would take some time in another video to derive those equations. So that's what we're going to do today. And I want to start with the equation for the sum of an arithmetic series. So what I'm going to do to start is I'm going to say that the sum of n terms is equal to 1 plus 2 plus 3. I'm just assuming that's the pattern, right? You add 1 each time. And then you're going to keep going until you get to plus, and you're going to have n as your last term, right? So I'll write it like this actually, n minus 1 plus n. So n is your very last term. N minus 1 is just the term before that, right? If you want to include the term before that, you could put n minus 2. And then in between, you have every other number. Now, that's one way to write this. I could also write it in reverse if I wanted to, right? I could write it as n, right? So the last number plus the number that comes before that, n minus 1, okay? And then plus the one that comes before that, right? N minus 2, plus, and then you leave a bunch of room here for all the other numbers, and then you get plus 2 plus 1, right? So I'm just writing this thing in reverse order. Now, what I could do is I can add these two things together. And if you add them, what's going to happen is the sum plus the sum is 2 times the sum, like that. And if you start adding things together, what do we notice? Well, you have 1 plus n is 1 plus n. You have 2 plus n minus 1. Okay, so plus 2 plus n minus 1, like that. Then you have plus 3 plus n minus 2. And that's going to keep going. And at the very end, you're going to have n plus 1, right? So I'm not going to write all the terms, but I wrote enough of them, and I wrote the last two. Well, if you notice, you can kind of group these things together, right? Like I could say these two go together, so 1 plus n. I can say that these three things can go together. 2 minus 1 is plus 1, so that becomes n plus 1. I can put these three together. 3 minus 2 is also plus 1, so you get n plus 1. And that's just going to keep going. And then at the very end, you see you have another n plus 1, right? It's n plus 1. So all you have is 2 times the sum is equal to a bunch of n plus 1s. In other words, you could say, instead of just a bunch of n plus 1s, you have as many of these as you have terms. So instead of writing a whole bunch of them, you can just write n, the number of terms, times n plus 1 or 1 plus n, however you want to write that. That's equal to 2 Sn. So now you're trying to solve for the sum, right? You want to know what the sum is equal to, so just divide both sides by 2. So you get the sum of n terms is equal to n, 1 plus n over 2. And in this case, 1 is just the placeholder for that first term, right? The first term in the series up here was 1, right? Right here. And so really the general form that you could write for this is the sum of n terms is equal to n times an, so the last term, the nth term, plus a1 being the first term, all over 2. So that's one way you can come up with this equation, right? There's other ways, like we talked about in the last video, where all you're doing is taking the average of the first and last term, right, by adding them divided by 2 and multiplying by the number of terms. So by taking the average, you're finding the average value really of every single term in between, and then you multiply that by the number of terms to get the sum. So that's another way to think about it, but this is your truly most mathematical, I would say, way of deriving this formula. And then there's another, actually, summation equation that we showed in the last video, and the way we came up with that was simply by saying that, well, your nth term is equal to your first term plus n minus 1 times d, right? And so you can plug this into this formula to get that other formula that we looked at. So Sn equals n times, instead of a to the n, you plug this in. So a1 plus n minus 1 times d plus a1 all over 2. And if you notice in that bracket, you have two A1s. You can put those together. So the sum is equal to n times 2A1 plus n minus 1 d over 2. So this is just another version of that same equation, right? So you would use the previous one up here if you know the first term and the last term, and you would use this equation here if you know the first term and not the last term, but the number of terms that you have, n, and you also know the d, right? The number that you add each time to get to the next term. So this will take care of that for you. We can do some examples just to show how this works. We could say that we have something like negative 50, that's your first term, plus negative 44, plus negative 38, plus, and then that just keeps going until you get to 2044, we'll say. And if you notice the pattern here, you're just adding 6 each time. So 6, that's the d value. And so if you want to find the sum of this series here, all you have to say is the sum is equal to a1 plus a2 divided by 2 times n, right? This is the equation that we just came up with earlier, right? The first one up here. So we can plug in our values, right? We know the first term is negative 50. We know the last term is 2044. Divide those by 2, and then multiply by the number of terms we have. Well, how many terms do we have, right? We don't actually know that right now. I can see 3 here, but then we skip a whole bunch before you get to the end. So how can I figure this out? Well, what you're going to want to do is take your last number, 2044, subtract the first number, which is negative 50. That's going to tell you the distance between the first and last number. And if you do that, you get 2094. Take that 2094 divided by the d value of 6. That's going to tell you how many times you're jumping, to the next term. It's going to tell you how many terms you have, and you get 349. Now, one thing to keep in mind, though, is that that's the number of jumps. So if this was 1, it would tell you jumped once, but that would mean you're at the second term. So really, we have to add 1 to this in order to get the total number of terms. So n is equal to 349 plus 1. So n is equal to 350. So that's how many terms we truly have here. Okay? So this is an important process to find n. So just plug in 350. Then we can calculate this, and that's going to give you 348,950. That's the sum if you add up all these numbers. Even though you don't know every single particular number in between, you could find them, but it's not really worth it, right? Instead, you can just use this equation, and you can find the sum. Another example would be if they told you something like AI is equal to AI minus 1 plus 11. So this is the implicit or recursive notation, right? And then they tell you that A1 is equal to 4. So we know the first term, and based on this top part, we know that you add 11 to each term to get to the next one. All right, that's what they're telling us here. And so let's say they ask us to find the sum of the first 650 terms of the series. How could we find that sum? Well, the first thing that we're going to have to do is say, well, the first term is 4, so to find an, your equation would be 4 plus 11 times n minus 1, right? 11 is the d value, you get it from there. So this is the equation to find any particular number. So we could find the 650th number, right? The last number. And so to find the last number, you just plug in 650 for n. So 4 plus 11 times 650 minus 1. Calculate that, you get 7,143. So that's the last term. First term is 4, last term is 7,143. You go up 11 each time. With all that information, I think we can find the sum of the first 650 terms, right? You just say 4 plus 7143 divided by 2 times the number of terms we have, which is 650. Calculate that, and you're going to get 2,322,775. That's the sum. Okay? Now, let's do another derivation. And for this one, we'll do the geometric sum, right? So the sum of the geometric series. So we'll start by saying Sn equals, so a will just be the first term, and then the second term is a times r, right? Because you multiply by r to get the next term. Well, you multiply this by r to get the term after that, so ar squared, and then it'll be ar cubed, ar to the 4. That keeps going until you get to ar to the exponent. So you're going to put n because n is the number of terms. But if you notice, the first term doesn't have any r's. The second term has 1, right, an exponent of 1. The third term has an exponent 2. So the term has one less exponent than the term itself. So the nth term would have n minus 1 as the exponent. Does that make sense? So now that you have this, you could say, all right, now I'm going to multiply that entire series by negative r. Okay, so bear with me here. Let's see what happens. Well, you get negative ar minus ar squared minus ar cubed, right? And that's going to keep going until you get to the end, and you'll have negative ar n minus 1 minus ar to the n, right? Because if you multiply this last term by negative r, it becomes negative, but also you add the exponents, right? N minus 1 plus 1, you would get n. If you recall your exponent rules, r to the 1 times r to the n minus 1, add those exponents together, you get r to the n, right? The ones cancel. That's why this becomes your last term. Now, what do we do with these? Well, let's add them together. So Sn minus Rsn is just going to be Sn minus Rsn. You can just write it like that. And then on the right here, you're going to see a lot of things happen, right? A lot of things are going to cancel out. Ar and minus ar squared and minus ar squared. That's going to continue for all these terms. This term and this term are going to cancel. All you're left with are the first term and the last term of this one. So you're going to have a minus ar to the n. Okay, so what happens? Well, let's solve for the sum. So on the left-hand side, you can factor out the sum, and you'll be left with 1 minus r equals a minus ar to the n. If you want, you can even factor an a out of the right side, so a 1 minus r to the n. And then on the left side, divide by 1 minus r. Do it on both sides to get rid of it. Just like that. Now this is the equation for the sum of a finite geometric series. And I say finite because n means you have a particular number of terms, right? So it doesn't go on forever. It's a set number of terms. It's finite, okay? Now, we can do an example of this, right, where we use this equation. I could say to find the sum of the first 50 terms, and the series I'm describing is going to be 1 plus 10 over 11 plus 100 over 121, and that keeps going. And if you ask yourself, what am I multiplying by each time? Well, I'm multiplying by 10 over 11, right? Multiply by 10 over 11. Keep doing that, right? Now, what is this going to turn into, right? When I take the sum of this, what is this equal to? The first 50 terms. Well, the sum of the first 50 terms will equal 1 times 1 minus r, which in this case is 10 over 11, to the exponent of 50 divided by 1 minus r, which is 10 over 11. If you calculate this, you're going to get approximately 10.906. It's going to keep going. So this is approximately your answer, right? Something like that. And if you wanted to, you could technically do this manually. You could type in the first 50 terms and add them together, although that would be a bit of a hassle, right? So that's why we use this equation. Another example would be if you had something like a1 equals 10, so they told you the first term, and then they told you that ai is equal to ai minus 1, so the previous term multiplied by 9/10. Okay, if they told you something like this, then you could figure out what the pattern looks like, right? You could say, all right, well, we start with 10, and then you add 10 times 9 over 10. And then you take that term and you multiply it by 9 over 10 again, so it would be 10 times 9 over 10 squared, right? And then you multiply by 9 over 10 again, so you'd have 10 times 9 over 10 cubed. And that would just continue, right? That would just keep going. And let's say that you want to find the sum of the first 30 terms, right? So you say, okay, sum of the first 30 terms. You do the exact same process, right? You do a, which is 10, multiplied by 1 minus 9 over 10 to the exponent of 30, because we're doing 30 terms, divided by 1 minus 9 over 10. And if you calculate this, you're going to get approximately 95.76, and that keeps going, right? So that's your approximate answer. Now let's talk about the equation for an infinite geometric series. So this is a geometric series that just continues forever, right? There's no set number of terms. And sometimes you're able to find what the series converges to, or in other words, what it adds to if it just continues forever. So we'll say that we have an infinite series here where we have a as your first term plus a times r to the 1 plus a times r squared, right? And that just continues forever, right? And then you're going to put down here r times s infinity, right? The sum of the infinite series. And so you multiply these all by r. So you'll have ar plus ar squared plus ar cubed, right? And that just goes on forever. And let's say you subtract these two things. So you have the infinite series minus this, so you can just write that like that. And then you subtract all these, right? So that minus that is 0, so they cancel. Now those are going to cancel. There's another term here that's r cubed that's going to cancel with this. They just keep canceling out forever, and you're just left with a, right? Your very first term. If you want to solve for the infinite sum here, you just say you have the sum times 1 minus r, right? You factor out that s, that's equal to a, divide both sides by 1 minus r, and you get the sum is equal to a over 1 minus r. That's the equation, right? That's the equation or the formula for the infinite series, or the sum of the infinite series. Okay? Now, one thing that's important about this is this will only converge, or in other words, it'll only give you a number, right? It'll only give you an answer if the absolute value of r is less than 1, or in other words, r has to be in between -1 and 1. Okay, so you can't be multiplying by 1 or 2 or 3 or 4, or -1 or -2 or -3, anything like that. It has to be either a half, or like -1/4, or -1/3, or +4/5, or something like that. Okay, that's the only way this is actually going to converge. And the reason for that should make sense, right? Because if you're just multiplying by a number like 2, then every term is going to be bigger and bigger and bigger. So if you add them all up, it just keeps getting bigger and bigger. It doesn't converge to a number. But if you add numbers that get infinitely smaller, because you're multiplying by a fraction that's less than 1, that's going to allow the numbers to get so small that you'll never get past a particular point, right? So let's do an example of this, and I'll show you what I mean. Let's say you're asked to find the sum, this is a summation symbol, from k equals 0 to infinity. And the function you have is 5 times 3/5 to the k. So what that means is that you use this function and you start with k being 0. Well, if k is 0, this whole part is just equal to 1, so you just have 5 as your first term. So this is just another way that these series can be expressed. So you have 5 plus, okay, now k is going to be 1, so 5 times 3/5, that's equal to 3. Okay, now k is going to be 2, so you have 5 times 9 over 25, because that's being squared, so that's going to be 9 over 5. The next term is going to be 27 over 25. That's just going to keep continuing forever, okay? Now the question is, what does this all add up to? Well, you can say, I'm going to just go ahead and use that formula. So I'm going to plug in the first term, which is 5, divided by 1 minus r. Well, the number you're multiplying by each time is this thing, right? 3/5. So 1 minus 3/5. If you calculate this, you're going to get 12.5. So if you add up all these numbers, they're all going to add up to 12.5 if you continue to infinity. So that's what the series converges to. And there are other ways to prove that, right? You can use limits, you can use different sorts of methods, but I would say that is probably the most straightforward way of seeing it. And of course, if that r value is greater than 1, if it's something like 3 or -4 or anything like that, then you would just state that the series does not converge. In fact, you would say that instead the series is divergent. And therefore you can't figure out what the sum is adding to as a nice answer.